In Q3 of 2023, a mid-sized financial institution integrated a cloud-hosted LLM into its internal compliance review pipeline. Every document query, including client tax records and account identifiers, was routed through a third-party API endpoint. During a regulatory audit, examiners flagged that PEA had traversed an external network boundary without explicit data processing agreements in place. The result: an emergency architecture rollback, a six-figure compliance penalty under HIPAA equivalent financial data regulations, and 3 months of re-engineering. Here is what made this incident systemic, rather than accidental. The engineering team had followed every documented best practice for cloud integration: rate limiting, TLS in transit, and role-based access. But no one had asked the foundational question: should this data ever leave the device or the on-premise perimeter at all? That question, where does inference happen, is the single most consequential architectural decision in any AI deployment today. And by the end of this lecture, you will have a formal framework to answer it before you write a single line of integration code. Now, you might think this is an outlier, compliance team that missed a checkbox. But consider the structural dynamics that make this fault risk, not an exception. First, cloud LLM integration has near zero friction. An API key, a few lines of SDK code, and you have GPT-4 or Gemini inside your product in under an hour. That speed eliminates the architectural review gate that normally catch data residency conflicts. Second, compliance mandates, GDPR Article 44, HIPAA's Business Associate Agreement requirements, South Korea's Personal Information Protection Act, all impose extraterritorial data transfer restrictions that are jurisdiction-specific and frequently updated. A cloud AI vendor's data center location can invalidate your compliance posture overnight when regulations change. API latency introduces a hard dependency on network availability. In healthcare edge devices, industrial IoT controllers, or offline-capable mobile applications, a 200 to 800 millisecond round trip to a cloud endpoint is architecturally unacceptable. And fourth, this is the most dangerous trap. Cloud AI creates architecture lock-in disguised as flexibility. The moment your prompt engineering, fine-tuning, and outputting logic are coupled to a specific vendor API schema, migration cost becomes a strategic liability. These four forces, compliance exposure, data residency conflict, latency dependency, and vendor lock-in, are not bugs in cloud AI. They are structural properties of the paradigm. The question is whether your architecture acknowledges them. And most teams, right now, do not. So here is exactly what this lecture will give you. Not a product comparison, not a benchmark table, but a decision-grade architecture framework. Across 6 chapters, we will dissect both paradigms at the component level, quantify their trade-offs on 5 axes, and anchor every theoretical point to real deployment constraints. By the time you reach the final chapter, you will be able to sit in an architecture review meeting and justify, with documented rationale, whether a given AI workload belongs on-device, on-premise, or in the cloud. The 5 evaluation axes we will use are directly mappable to the 정보 examination framework: availability, security, performance, cost, and scalability. We will apply these axes to Google's newly released LiteRT-LM runtime, quantized model formats like GGF and Executorch, and to domain-specific scenarios in healthcare, finance, and industrial IoT. Each axis is not a preference. It is a measurable constraint with a threshold. For example, if your security requirement is no data leaves the device perimeter, that is not a preference for on-device AI. It is a binary architectural gate that eliminates cloud as an option entirely, regardless of cost or capability. That kind of crisp, defensible reasoning is what separates a senior architect from a developer who picked the first API that worked. In the next chapter, we define the 2 paradigms from first principles, and you will immediately see why the standard mental model most teams use is incomplete. Let's dissect exactly what happens when your application calls a cloud LLM. The journey begins the moment a user prompt leaves the device. First, it hits an API gateway, the entry point that handles authentication, rate limiting, and request routing. From there, the request traverses the public internet, or a private WAN link to reach a load balancer sitting in front of the inference cluster. That cluster is a fleet of high-end GPUs, typically NVIDIA L100s or H100s, running a model inference server like Triton or VLLM. The model processes your tokens, and the response streams back token by token through the same reverse path. Every single hop in this chain, DNS resolution, TLS handshake, gateway processing, queuing, inference time, and return streaming, accumulates latency. And critically, your raw prompt data crosses multiple organizational and network boundaries before a single token is generated. That boundary crossing is not just a latency problem, it is a compliance and sovereignty problem. But the latency story gets even more uncomfortable when we look at what the inference server is actually doing under the hood. The latency numbers we just traced are not accidents. They are the direct consequence of the architectural assumptions Cloud LLM designers made from day one. Cloud LLM is built on three foundational assumptions. First, compute is shared. Thousands of tenants run inference on the same physical GPU cluster, which makes unit economics viable but means your workload competes with everyone else's. Second, the model is centralized and versioned on the provider's schedule. When OpenAI updates GP4, you absorb that change whether you planned for it or not. Behavior drift is a real production risk. Third, scaling is elastic and treated as the primary value proposition. Cloud can burst from 10 requests per second to 10,000 with no infrastructure work on your side. But here is the architectural catch that rarely appears in vendor slide decks. Cold start. When your traffic pattern is bursty or low volume, the inference server may need to load model weights from storage into GPU VRAM before it can serve your first request. For a 70 billion parameter model, that weight loading can take tens of seconds. These three assumptions, shared compute, centralized versioning, and elastic scaling, define what Cloud LLM is optimized for. And by extension, they define exactly where it fails. Next, we flip the architecture entirely and see what the on-device paradigm assumes instead. Now let's define on-device LLM architecture with precision, because the term is used loosely in the market, and that imprecision causes bad architectural decisions. On-device LLM means exactly this. The entire inference computation, tokenization, embedding lookup, all transformer forward passes, and detokenization executes within the hardware boundary of the end-user device. No token, no embedding, no intermediate activation ever leaves the silicon. This is not a performance optimization. It is a fundamentally different compute contract. The implications are architectural, not incremental. Consider what this means structurally. The model waits live in device local storage, typically flash memory. During inference, those weights are loaded into the device's local memory, LPDDR5 on mobile, unified memory on Apple Silicon. The compute happens on the device's NPU, GPU, or CPU depending on hardware generation, and the result is returned to the calling application without any network transaction whatsoever. This architecture eliminates the network round trip entirely, which collapses first token latency from hundreds of milliseconds to single-digit milliseconds on modern NPU hardware. It also eliminates data egress by definition. There is no mechanism for the prompt to leave the device. But wait, if this is so clearly superior on latency and privacy, why isn't every application using it? The answer lies in the software stack, which we will examine next. Defining the on-device compute contract is necessary but not sufficient. The harder engineering problem is, how do you actually run a model that was trained on a 1,000 GPU cluster on a device with 4 GB of addressable RAM and a 15-watt power envelope? The answer is a layered software stack, and understanding each layer is essential for any architect designing on-device AI systems. At the top sits your application, iOS, Android, or embedded firmware. Directly below is the runtime engine layer. This is where Google LiteRT-LM, Apple Core ML, and Qualcomm QNN operate. The runtime engine is responsible for executing the computation graph of the model. Below the runtime is the hardware abstraction layer. It translates the runtime's generic operator calls into NPU-specific instructions, handling the dramatic differences between Apple's ANI, Qualcomm's Hexagon DSP, and MediaTek's APU. At the foundation sit the quantized model weights, the result of taking a full precision model and compressing it via INT4 or INT8 quantization, reducing a 7 billion parameter model from 14 GB in FP16 down to roughly 3.5 GB in INT4. Each layer introduces its own engineering constraints and failure modes. This stack is why on-device LLM is not simply download a model and run it. It is a full systems engineering discipline. And in our next chapter, we will use this architecture as the basis for a 5-axis trade-off matrix that tells you exactly when to choose which paradigm. The on-device LLM stack we just described did not appear overnight. It is the product of a decade of compounding advances across hardware silicon, compression algorithms, and runtime engineering. Understanding this evolution is critical because it tells you which constraints are permanent and which are still moving, and that distinction drives your architecture's longevity. In 2017, TinyML established the proof of concept, neural networks small enough to run on microcontrollers with kilobytes of RAM. Useful for keyword detection, not for language reasoning. In 2019, Google shipped TensorFlow Lite, or TF Lite, which brought quantized inference to Android and embedded Linux with NPU delegation support. This crossed the threshold for on-device vision and audio models. Between 2020 and 2022, Apple's Core ML alongside the A14 and M1 chips which introduced dedicated neural engine blocks, delivering 16 trillion operations per second, the first consumer hardware capable of plausible language model inference. The decisive inflection came in 2023 and 2024. Model distillation techniques, pioneered in papers like Dissected and then industrialized for decoder-only LLMs, showed that a 3-parameter model could achieve 80% of a 70-parameter model's benchmark performance at 5% of the memory footprint. Then in 2025, Google launched LiteRT-LM, the first production-grade, runtime purpose-built for on-device LLM execution, completing the stack from quantized weights all the way to Android and iOS application APIs. The viability threshold has been crossed. The question is no longer can we run LLMs on-device. It is for which workloads should we, and what do we trade away when we do? That is exactly the 5-axis framework we build in the next chapter. Let's start with the trade-off every architect feels immediately: latency. For a cloud LLM, your request travels from device to CDN edge, routes to a GPU cluster in an inference queue, generates tokens, and streams the response back. Under ideal 5G conditions, that round-trip floor is roughly 200 to 400 milliseconds before the token even appears. Add network jitter, a busy queue, or weak Wi-Fi signal, and you're looking at 1 to 3 full seconds of dead silence. On-device inference, by contrast, has zero transit time. The first token emerges from local silicon at 150 milliseconds on a modern NPU. But here is the reversal that surprises most engineers. On a low-end device with no dedicated NPU, on-device inference can be slower than cloud for long context generation. The on-device always wins on latency assumption is a dangerous oversimplification. The decisive win for on-device is offline resilience. In a tunnel, on an aircraft, or in a factory floor with no connectivity, cloud LLM simply returns an error. But the cost of that resilience is a hard constraint on model capability, and that constraint is what we quantify next. Now let's talk about cost, because this is where the business case either closes or collapses. Cloud LLMs bill per token. GPT-class models run at roughly $10 to $30 per million out tokens. At modest enterprise scale, say 10 million queries per month, averaging 500 output tokens each, you are spending $50,000 to $150,000 monthly purely on API fees. That number compounds annually and scales linearly with usage growth. On-device deployment has a radically different cost structure. You pay once for model optimization and integration engineering, typically a $50,000 to $200,000 one-time investment. And then your marginal cost per inference is essentially zero, amortized across the device fleet. The break-even threshold depends critically on query volume and query frequency. Our TCO model shows that for applications exceeding roughly 5 million queries per month sustained over 12 months, on-device deployment pays for itself. Below that threshold, Cloud API remains more economical when you factor in the engineering overhead of on-device maintenance. But here is the critical variable most TCO models miss. What happens when your API provider changes pricing? On-device gives you cost predictability that cloud can never guarantee. And cost predictability in enterprise procurement is often worth more than raw cost efficiency. Latency and cost are visible trade-offs. Engineers debate them openly. But the trade-offs in this section are architectural eliminators. They don't create a preference. They make one option legally impossible. Consider healthcare. Under HIPAA in the United States, any system that transmits protected health information to a third-party server triggers a business associate agreement obligation, mandatory breach notification procedures, and audit logging requirements. A cloud LLM provider that processes patient data, even transiently in memory, becomes a business associate. Many providers refuse this liability. The architecture is dead before it ships. In Europe, GDPR 44 prohibits transferring personal data to jurisdictions without adequate protection. In South Korea, the Personal Information Protection Act imposes similar data residency constraints. In finance, PCI DSS requires that cardholder never traverse untrusted networks. For all of these use cases, on-device inference with zero data egress is not a technical preference, it is a compliance mandate. The data never leaves the device. There is no transmission to intercept, no third-party server to audit, no data residency ambiguity. The architecture itself is the compliance control. But wait, does keeping the model on-device automatically make the system secure? The answer is more nuanced than most architects expect. Now let's map the actual attack surfaces. Because security is not binary, and on-device is not automatically safer. Cloud LLM deployments expose a classic network threat model, data in transit between client and API endpoint, prompt injection via malicious user input that hijacks the model's instruction context, and the risk of response interception or replay attacks. The API key itself becomes a high-value credential, leaked once, and your entire inference budget is compromised. On-device deployments eliminate all transit exposure. There is no network path to intercept, but they introduce a threat vector that cloud completely avoids: model theft. A quantized 7 billion parameter model stored on a consumer device can be extracted by a motivated attacker with physical access. Your proprietary find model, representing potentially millions of dollars in training investment, becomes vulnerable to intellectual property theft. The defense is trusted execution environment isolation, where TE enclaves like ARM Trust Zone protect model weights in secure memory that even the device OS cannot read. However, TE integration adds significant engineering complexity and is not universally available across device tiers. The honest security comparison is: Cloud LLM has a larger network attack surface, but stronger model IP protection. On-device has zero transit exposure, but requires explicit TE architecture to protect model IP. The threat model determines which risk profile your organization can accept, and that decision is what separates good architecture from naive architecture. We have covered latency, cost, and security. Now we hit the constraint that is most technically unforgiving: model size. This is where the physics of on-device deployment become non-negotiable. A full precision GPT-4 class model runs to hundreds of billions of parameters, requiring hundreds of gigabytes of storage and VRAM. That simply does not exist on a mobile device. The practical ceiling for on-device deployment today is 7 billion parameters, and even that requires aggressive quantization. INT-wheat quantization reduces memory footprint by roughly 50% compared to F32 baseline. INT-water quantization cuts it by 75%. A 7 billion parameter model in FP32 occupies approximately 28 gigabytes. In INT8, that drops to 7 gigabytes. In INT34 at 3.5 gigabytes, which fits within the RAM budget of a flagship smartphone. But quantization is not free. INT4 models show measurable degradation on complex reasoning benchmarks, typically 3 to 8 percentage points on MMLU compared to FE32 equivalents. For IoT microcontrollers with 512 kilobytes of RAM, even INT4 7 billion parameter models are completely off the table. The practical on-device tier for IoT is sub 1 billion parameter models, specialized, narrow, and purpose-built. The parameter count ceiling is not an engineering challenge you solve with cleverness. It is a thermodynamic constraint on what intelligence you can deploy at the edge. The final axis is operational agility, and this is where on-device deployments reveal their most underestimated hidden cost. In cloud, updating a model is a server-side operation. Your team pushes a new model version to the inference cluster, runs a canary deployment, validates quality metrics, and routes some percent of traffic to the new version, all without touching a single end-user device. Rollback is instantaneous. Redirect traffic back to the previous version. Total propagation time, minutes to hours. Device fleet management is a fundamentally different operational discipline. A model update means pushing a binary artifact of 500 megabytes to 3.5 gigabytes every device in your fleet, potentially millions of endpoints. Over-the-air update infrastructure must handle partial downloads, resume logic, version conflict resolution, and battery-aware scheduling. A user running version 0.2 of your model, while your cloud backend expects version 3, creates schema mismatches that break your entire application. Rollback means re-pushing the old model binary, another multi-gigabyte transfer. And if 5% of your fleet fails to update due to storage constraints, you are permanently running a heterogeneous model environment. This is not a theoretical concern. It is the operational reality that has caused multiple enterprise on-device AI initiatives to fail silently, not from model quality issues, but from fleet management complexity. As we move into the next chapter, we will see exactly how Google's LiteRT-LM architecture attempts to solve this update agility problem at the framework level, and whether the solution holds up under real-world constraints. Let's crack open LiteRT-LM and look at exactly what's inside. Google's runtime is organized as a strict 4-layer stack. At the top sits the model bundle, a flat buffer serialized artifact containing weights, tokenizer vocabulary, and graph metadata in a single portable file. Below that is the runtime abstraction layer, which presents a unified inference API regardless of the target platform. The third layer is the hardware delegate router, responsible for dispatching compute graphs to the optimal accelerator. And at the base are the platform backends: Android and NAPI, iOS Core ML, WebAssembly with WebGPU, and embedded Linux via OpenCL. This separation is architecturally deliberate. It mirrors the classic ISO OSI principle of layer independence. Each layer can evolve without breaking the contract above it. The critical insight here is that the model artifact never changes, only the backend does. But here is where it gets interesting. That hardware delegate router makes decisions at runtime that can dramatically alter your latency profile. and the rules it follows are more nuanced than most engineers expect. Now let's trace an actual inference request through LiteRT-LM step by step, because this is where the constraints of edge devices become brutally visible. Step 1 is tokenization. The input text is converted to token IDs entirely on device using the bundled sentence piece vocabulary, no network call, no cloud lookup. Step 2 is prefill. All input tokens are processed in parallel to populate the KV cache. This is the most compute-intensive phase, and on a mobile NPU it can take hundreds of milliseconds for long prompts. Step 3 is the decode loop. The model autoregressively generates one token at a time, reading from and writing to the KV cache on each step. This is memory bandwidth bound, not compute bound, a critical distinction when sizing your device target. Step 4 is detokenization. Token IDs are converted back to text and streamed to the application layer. The KV cache is the architectural linchpin here. On cloud servers, KV cache lives in GPU HBM with hundreds of gigabytes available. On a mobile device, you might have 4 to 8 megabytes of NPU local SRAM. Constraint dictates your maximum context length, and it cannot be engineered away. The question then becomes, how do you design your application knowing the context window is a hard physical limit? The hardware delegate abstraction is one of LiteRT-LM's most strategically important engineering decisions. Instead of requiring developers to write platform-specific inference code, LiteRT-LM implements a priority-ordered fallback chain, NPU delegate first, GPU delegate second, CPU fallback last. The delegate router performs an operator coverage, check-it model load time. If the NPU cannot execute a particular op, that op is silently offloaded to the GPU or CPU. This graceful degradation means a single binary runs on a flagship device with a dedicated NPU and on a budget device with only a CPU, with no code changes. From a systems architecture perspective, this maps directly to the Liskov substitution principle applied at the hardware abstraction layer. But here is the architectural warning: silent fallback can destroy your latency SLA. 30% of your model ops fall back to CPU because of an NPU driver gap you may never know without explicit profiling. The next section on quantization reveals exactly why op coverage gaps happen, and how compression choices directly determine which ops land on which hardware. Quantization is the single most impactful lever for deploying LLMs on constrained devices, and understanding the INT4 versus INT8 trade-off is non-negligible for any architect making a device selection decision. Let's put the numbers on the table. A Gemma 2B model in full FFP32 precision requires approximately 16 gigabytes of storage, impossible on any mobile device. INT8 quantization reduces this to 2 gigabytes. With typical benchmark accuracy loss of 1 to 3% on standard NLP tasks like MMLU and HelloSwag, INT4 quantization cuts it further to 1 gigabyte, enabling even mid-range devices, but accuracy loss climbs to 4 to 8% depending on the task domain. Critically, INT4 also delivers a 30 to 50% sprint speed improvement over INT8 on NPU hardware because of reduced memory bandwidth pressure. The architectural decision rule here is not simply use INT4 because it's smaller. For general-purpose chat applications, INT4 is often acceptable. For medical diagnosis assistance or legal document analysis, domains where hallucination cost is high, INT8 or hybrid quantization may be mandatory. This is exactly the kind of trade-off that appears in information systems architect examinations under the heading of non-functional requirement prioritization. But wait, quantization alone is not enough to reach deployment size targets. The compression pipeline has 2 more stages that most engineers overlook entirely. Quantization is the final step of a 3-stage compression pipeline, and understanding all 3 stages is what separates architects who deploy successfully from those who hit a wall at the last meter. Stage 1 is knowledge distillation. A large teacher model, say Gemini 1.5 Pro, supervises the training of a smaller student model, transferring behavioral knowledge rather than raw weights. This is how Gemma Nano achieves performance disproportionate to its parameter count. Stage 2 is structured pruning. Attention heads and feed-forward neurons with consistently low activation magnitude are identified and permanently removed. Google's research on Gemma Nano reports 20 to 30% parameter reduction, with under 2% accuracy loss when pruning is applied after distillation. Stage 3 is post-training quantization, which we analyzed in the previous scene. The order matters architecturally: distillation first, then pruning, then quantization. Reversing this sequence degrades accuracy significantly because quantization noise compounds on top of pruning-induced sparsity. The output of this pipeline is a LiteRT-LM compatible flat buffer artifact ready for deployment. The key realization is that this pipeline is a one-way transformation. Once compressed, the model cannot be trivially re-expanded. Your deployment artifact is a permanent architectural commitment. In the next section, we examine what happens when that committed artifact meets the reality of cross-platform deployment. The marketing promise of LiteRT-LM is compelling. Write once, deploy anywhere, Android, iOS web browsers, and embedded Linux from a single flat buffer model bundle. Let's map exactly how that promise is architected. The center of gravity is the flat buffer model format, which is both platform neutral and zero-copy deserializable, meaning the runtime can memory map the model file directly without parsing overhead, a critical performance advantage on storage-constrained devices. From that single center, 4 deployment targets branch out. On Android, the model is loaded via the Android NDK and dispatched in an API for hardware acceleration. On iOS, a Core ML bridge translates LiteRT ops to Apple's native graph format, enabling neural engine acceleration. For web deployment, the model runs inside a WebAssembly sandbox with Web GPU, providing GPU acceleration where supported. For embedded Linux, think Raspberry Pi or automotive ECUs. OpenCL or XNenPack provide the compute backend. From a systems architecture standpoint, this is a textbook application of the abstract factory pattern at the infrastructure layer. The model artifact is the product. Each platform backend is the concrete factory. But here is the question that every architect should be asking right now. If the model and the API are identical, why do production deployments on different platforms exhibit such dramatically different behavior? The write once promise breaks down in 3 specific and predictable ways, and every architect deploying LiteRT-LM at scale needs to treat these not as bugs but as hard architectural constraints. First, iOS sandbox restrictions. Apple's App Store entitlement model prohibits JIT compilation and restricts dynamic library loading. This means certain LiteRT-LM ops that rely on runtime code generation fall slower interpreted paths, grading decode throughput up to 40% compared to Android on equivalent hardware. Second, browser memory caps. The WebAssembly linear memory model imposes a 4 GB address space ceiling, and many browsers further restrict this to 2 GB in practice. A quantized Gemma 2B at 1 GB of weights plus KV cache overhead can easily breach this limit at longer context lengths. Third, embedded Linux driver gaps. On non-tier 1 silicon, industrial microcontrollers, older automotive SoCs, OpenCL driver quality varies enormously, causing op coverage failures that silently route large portions of the graph to CPU. The architectural discipline required here is identical to what IEC Q5 calls portability subcharacteristics. Adaptability, installability, and replaceability. Each platform gap must be explicitly tested and mitigated in your deployment pipeline, not assumed away by the runtime. This brings us to the pivotal question for Chapter 5. Given these platform-specific constraints, how do you select the right architecture for your specific domain? The domain-specific selection guide answers exactly that. Let's start with a legal reality check. In financial services, GDPR Article 25 mandates data protection, meaning we must never leave the device boundary if processing can be performed locally. The same logic applies under HIPAA's minimum necessary standard in healthcare. Patient data transmitted to a cloud inference endpoint creates an auditable data flow that regulators will scrutinize. This is not a performance decision, it is a compliance-forced architectural choice. On-device LLM inference eliminates the transmission event entirely, collapsing the audit surface to a single trust boundary, the device itself. Financial document classification, transaction anomaly tagging, and clinical note summarization all share this property. The sensitivity of the input data makes cloud routing legally indefensible without explicit consent and business associate agreements. The architecture answer writes itself: zero trust edge, where the model, the data, and the audit trail never leave the device perimeter. But here is where it gets technically interesting. Enforcing this boundary in practice requires more than just running a model locally. The next scene shows exactly what the reference architecture looks like. So what does a production-grade on-device RAG architecture actually look like inside a regulated environment? The pattern has 4 mandatory layers. First, the model bundle itself is AES-256 encrypted at rest and decrypted only within the secure enclave. On Apple Silicon, this is the T2 or M series secure element. On Android, it maps to Strongbox. The encryption key never exists in application memory. Second, the local vector store, typically a quantized face or SQLite vec index, stores document embeddings alongside their source documents, also encrypted using the same key hierarchy. Third, at query time, the RAG retriever runs entirely within process isolation. The query embedding, nearest neighbor search, and context assembly happen before any tokens are fed to the LLM. No intermediate state is written to unprotected storage. Fourth, the audit trail. Every inference call is logged to a tamper-evident local ledger using HMAC chaining. satisfying requirements ISO SU2 Type 2 and ISO and a Team 711 Annex A. The critical design constraint is that the secure enclave has strict memory limits, typically 4 to 8 megabytes. So the model itself lives in protected application memory with the enclave holding only the key material. But this raises an immediate operational question. What happens in an air-gapped manufacturing environment where even OS-level secure enclaves may not exist? That is exactly what the next section addresses. Now shift from the legal domain to the physical domain. On a manufacturing floor running CNC machines or a pipeline monitoring an offshore oil platform, connectivity is not degraded, it is absent by design. Air-gapped networks are the security architecture for OT environments under IEC C60443, the Industrial Cybersecurity Standard. Any architecture that assumes a network call to a cloud inference endpoint fails the availability requirement immediately. 100-millisecond cloud round trip to detect a bearing failure anomaly is 199 milliseconds too late when the failure event propagates in under 50 milliseconds. This is the fundamental mismatch between cloud LLM latency profiles and industrial real-time constraints. On-device LLM inference on an edge compute node, an NVIDIA Jetson, Occhip RK3348, or an industrial PC with an integrated NPU, eliminates the network dependency entirely. The LLM runs inference on sensor telemetry streams locally, producing anomaly classifications and maintenance recommendations without any uplink. Consider Siemens' deployment of Edge AI on SIMATIC IPC hardware. Local inference latency under 10 milliseconds for structured telemetry inputs with zero cloud dependency. The predictive maintenance use case is precisely where on-device wins on the availability axis. But managing of these devices, without a network, its own architectural challenge. Let's look at how the edge gateway pattern solves that. Managing a fleet of air-gapped edge devices running LLM inference creates a paradox. You need to update the model without a reliable network. The edge gateway pattern resolves this through a hierarchical deployment topology. At the top sits a central model registry, the single source of truth for versioned, signed model bundles. Below it, regional edge gateways act as local update brokers. When connectivity becomes intermittently available, perhaps via scheduled VPN windows or physical media like USB, in extreme cases, they pull and cache the latest signed model artifact. Individual IoT nodes then pull from their nearest gateway over the local OT network, never requiring a direct internet connection. For Model A/B testing on device, the pattern uses a shadow deployment flag. 50% of fleet nodes are silently assigned to model version B, while 80% on version A. Performance telemetry, inference latency, classification confidence distributions, anomaly false positive rates, is aggregated at the gateway level and compared. If version B shows degradation, a rollback signal is broadcast to all nodes via the gateway, reverting to the last known good model bundle using the cryptographic hash stored in the gateway's local registry. The critical design constraint here is that every model bundle must carry a digital signature verified against a hardware root of trust on each node, preventing a compromised gateway from pushing a malicious model. This entire pattern maps directly to NIST EST 800-93-3 Platform for Firmware Resiliency Guidelines. Now, with both regulated and connectivity constrained scenarios covered, the real question is, when should you choose on-device? That tension is where the most important architectural insight lies. Here is the counterintuitive move. After spending this lecture making the case for on-device LLM, let's be precise about where it unambiguously loses. There are three workload classes where cloud architecture remains architecturally superior, and confusing this boundary is how expensive mistakes get made. First, long context reasoning. Current on-device LLMs are constrained to 4K to 8K token context windows due to the KV cache memory footprint scaling quadratically with context length. A 128K TAE context GPT-4 class task, legal contract review, full codebase analysis, simply cannot execute on a device with 8 to 12 gigabytes of shared memory. Second, multimodal tasks. Processing high-resolution images or video frames alongside text requires parallel compute pipelines that exceed current mobile NPU architectures. A single 4K video frame inference pass on a mobile device takes 800 milliseconds to 2 seconds, making real-time multimodal interaction on-device impractical today. Third, rapid model iteration. If your product requires weekly model updates based on live user feedback, the standard A/B testing cadence for consumer AI products, on-device deployment latency, and update friction eliminate this agility entirely. The cloud's ability to update a model globally in under an hour is architecturally incompatible with on-device constraints. The trap architects fall into is binary thinking, on-device or cloud. But the strongest production architectures use both. The next scene shows exactly how to combine them without compromising the privacy guarantee. The synthesis of everything in this lecture is a single architectural pattern: tiered hybrid inference. The insight is elegant. Use on-device LLM not as a replacement for cloud, but as a privacy-enforcing pre-processing gate. Here is how it works in production. Step 1. The raw user input, which may contain names, account numbers, medical codes, or location data, enters the on-device LLM first. The on-device model performs two operations: PE detection and de-identification, replacing sensitive entities with semantic placeholders, and query complexity classification, determining whether the de-identified query exceeds the on-device model's capability ceiling. Step 2. If the query is simple and privacy-sensitive, the on-device LLM answers directly. The data never leaves the device. Step 3. If the query requires cloud-class capabilities, long context, multimodal, complex reasoning, the de-identified version is escalated to the cloud endpoint. The cloud LLM never sees the original PEA. It processes only the semantically equivalent but anonymized representation. Step 4. The cloud response is returned and repersonalized on-device by substituting the original entities back, using the local de-identification map. This pattern satisfies both the privacy constraint and the capability requirement simultaneously. It is the architectural answer to the false dichotomy between on-device privacy and cloud intelligence. In the final chapter, we will formalize this entire decision framework into an exam-ready matrix: 5 axes, 3 architecture classes, and the precise conditions under which each wins. That is the deliverable you have been building toward across all 5 chapters. We have now traveled through every architectural layer, inference engines, memory constraints, security boundaries, and domain-specific selection patterns. It is time to consolidate everything into a single, actionable decision instrument. The 5-axis trade-off matrix you see here is not a theoretical exercise. It is the artifact you bring into an architecture review board. Each axis is scored 1 through 5. On-device wins decisively on latency, privacy, and security, scoring 5, 5, and 4 respectively. Cloud wins on model size, headroom, and update agility, scoring 5 and 5 versus on-devices as 2 and 2. The critical insight: single architecture dominates all 5 axes simultaneously. This is the fundamental truth that separates senior architects from junior developers. When a stakeholder demands the best AI solution, your answer must always begin with, best on which axis? The matrix forces that conversation to happen explicitly, before code is written, before budgets are committed. Notice that the cost axis reveals a crossover point. On-device has high upfront hardware cost, but near zero per inference cost at scale, while cloud inverts that profile entirely. This crossover tip occurs around 10 million inferences per month for mid-tier hardware. Now, here is the question you must answer before your next architecture decision. Which 2 axes are truly non-negotiable for your specific use case? And does your current stack reflect that priority? Scoring the matrix is only step 1. The real architectural discipline is in what you do with the scores afterward. Here is the 3-step process for deploying this matrix inside a stakeholder architecture review. Step 1. Score every axis collaboratively with product, security, and infrastructure stakeholders, never alone. Disagreements on scores surface hidden assumptions. Step 2. Flag non-negotiables. Any axis where a stakeholder marks a requirement as absolute, for instance, security due to GDPR compliance, or latency due to a safety-critical response window, automatically constrains your architecture space. Non-negotiables are veto conditions, not preferences. Step 3. Document residual risks explicitly in a risk register. If you choose on-device to satisfy latency and security, document the residual risk that model updates will lag by days or weeks. If you choose cloud to maximize capability, document the residual risk of service degradation under network partition. This risk register is not bureaucratic overhead. It is your legal and technical shield when the architecture is challenged 6 months later. Remember, the matrix does not make the decision for you. It makes the decision auditable, repeatable, and defensible. That distinction is what separates a senior architect's deliverable from a developer's opinion. Now let us make this lecture directly exam-worthy. The Korean Information Management Professional Engineer Examination evaluates system architecture through 5 canonical evaluation axes: availability, security, performance, cost, and scalability. Every concept we have covered in this lecture maps precisely on or more of these axes. And that mapping is your answer structure template. Availability maps to on-devices offline resilience and cloud's redundancy clustering. Security maps to data locality, T-based attestation, and zero-trust network boundaries. Performance maps to inference latency, throughput under NPU acceleration, and quantization efficiency. Cost maps to the per inference versus upfront hardware trade-off and the TCO crossover analysis. Scalability maps to fleet management, OTA update pipelines, and elastic cloud inference capacity. Here is the critical exam insight. When a question asks you to compare edge AI and cloud AI architectures, the highest scoring answers do not simply list features, they explicitly state which evaluation axis each architectural choice optimizes and what the trade-off cost is on the opposing axis. Examiners reward structured trade-off reasoning above all else. Notice that federated learning, which we will flag as your next study topic, cuts across all 5 axes simultaneously, making it a premium exam topic in its own right. Let us walk through a sample exam question, exactly as it would appear in the Information Management Professional Engineer exam, and demonstrate the answer structure that earns maximum marks. The question reads, compare edge AI and cloud AI architectures from the perspectives of security, performance, and cost. Propose a hybrid architecture for a financial mobile application and justify your selection. A low-scoring answer lists features. A high-scoring answer follows this structure. First, define the architectural problem space. What makes financial application uniquely constrained? Second, analyze each evaluation axis explicitly, naming the trade-off direction and its magnitude. Third, propose the hybrid model, on-device inference for biometric authentication and local fraud pattern detection, cloud for complex anomaly models and regulatory reporting. Justify using the 5-axis matrix scores. Fifth, register residual risks, model staleness on device, data synchronization latency to cloud. Examiners award points for each of these 5 structural elements. The differentiator is the explicit trade-off cost statement on every axis, not just what you chose, but what you gave up to choose it. That is the intellectual rigor the exam rewards, and it is exactly the framework this entire lecture has been building toward. We have covered the complete architecture anatomy of on-device LLMs, from inference engine internals and memory hierarchy to security threat models, domain-specific selection patterns, and the 5-axis decision framework. Every keyword on this summary slide is a potential exam answer component, a stakeholder conversation anchor, or an architecture review criterion. You now have a complete mental model for answering the question this lecture posed at the outset. Not is on-device AI better than cloud AI, but under which conditions does each architecture deliver superior value, and what is the explicit cost of that choice? 2 topics stand at the frontier of everything we discussed. Federated learning resolves the tension between on-device privacy and cloud-scale model improvement. Training improves without data ever leaving the device, but it introduces new threat surfaces around gradient poisoning and communication overhead. Edge MLOps addresses the operational gap we repeatedly identified. How do you manage model versioning, A/B testing, rollback, and monitoring across a fleet of millions of heterogeneous devices? Both topics cut across all 5 evaluation axes and represent premium examination material for the next examination cycle. The on-device AI revolution is not a technology trend. It is a fundamental renegotiation of where intelligence lives, where data is owned, and who controls the inference boundary. Architects who can navigate that renegotiation with structured rigor will define the next decade of system design. That is the framework. Now go build something defensible.